and choose 4 equals 495, and I thought this was kind of an interesting problem. It's pretty straightforward, but the calculation I realized is kind of messy, so I wanted to see if I had a easier way to do this. So let's write out n choose 4 in a format that we can deal with a little better. So this is the same thing as saying n factorial over n minus 4 factorial times 4 factorial equals 495. And the first thing I want to do is I just want to bring this 4 factorial over here to simplify things a little bit. And what I'm going to do, let's write out the n factorial explicitly so it's a little easier to work with. So I'll write n factorial as n times n minus 1, just the definition of factorial, but we'll stop at n minus 4 so that we can get some cancellation going. So I'll write that as n minus 4 factorial. So that's going to be our definition of n factorial in the numerator. Then in the denominator, we're going to have n minus 4 factorial, and this is going to equal 495 times 4 factorial. This is where I thought it was kind of interesting because I was like, okay, 4 factorial is 24. But if I multiply that out, it doesn't help me. It's just going to create a big number. I think it's 11,880. And that doesn't stick out to me as something I want to deal with. So we'll leave it like this with the factorial in the expression, and we'll show you how that's going to be easier. So we'll cancel out the n minus 4 factorial. So then all we have is we're multiplying 4 consecutive positive integers, and we want it to equal 495 times 4 factorial. Now what we want to do with this on the right is we want to get the prime factorization. So without spending too much time, 495 is actually 5 times 99. If you think about it, if we wrote 5 times 100 minus 1, if we distribute, we'd have 500 minus 5, which equals 495. So for the prime factorization, 5 times 99, it's going to be 5 times 3 squared times 11. Then 4 factorial is just going to be a 3 and 2 to the third. And so let's just kind of clean this up a little bit. We're going to end up with 11 times 5 times 3 to the third times 2 to the third for the factorization. So the reason I'm doing this is because what you really want to do in this situation is you want to look for primes. So like the key giveaway is 11. So we know that we have to, in this expression, one of our integers has, one of these numbers has to be 11. We don't know which one. So what this means is we know that we have, in this expression, we know we have to have 11 or a factor of 11. And so what we can do is try to kind of piece together what this expression might be. The primes are usually a good giveaway if you have particularly the highest prime. And so we could have an idea that we have like an 11, a 5 and a 2 is a 10. And so for 4 consecutive integers, we could have something like 11 times 10 times 9 times 8. Now the problem with that is 8 is 2 to the third. And we have a 2 in this, so we know that this expression has 4 2's and we only have 3 2's to use over here. So that's going to be a little bit of a problem. And there's not really, we need to avoid this 8, because otherwise we're going to end up with too many 2's. So let's try 12 times 11 times 10 times 9. And so then we have 111, so this is going to break down as 11 times 5 times 2 times 3 squared. This 12 is going to be 3 squared, 2 squared. And if we clean that up, we can get this into a prime factorization. We're going to have 3. Oh, I made a mistake here. This is just a 3, not a 3 squared. So if we multiply this out, we're going to have a 3 to the third, 3 to the third, 2 to the third, right? We got 2 2's and a 1 and 1, so that's 2 to the third, 11, 5, and you'll notice this matches this exactly. So in the when the prime factorization matches exactly, that has to be the same number. So that's going to be our basically our answer. But the question wants n. So n in this is actually the largest integer in the 4 consecutive integers, so that is actually going to be 12. So our answer for this problem, n equals 12.